So in this video, I'm going to be going over variational calculus. So this is called variational calculus. So what is variational calculus? It's basically an optimization, finding the best curve that extremizes an functional. It's not an. Sorry, extremizes something called a functional. So find the best curve gamma that extremizes a functional. So this is called variational calculus, of course. Now the question is, what is a functional and what do I mean by a curve? And we'll define a functional to be a function takes a curve and produces a number. So for example, the most common functional that we're going to be interested in is basically an integral. So for example, if somebody says an integral that goes from x to b, but they don't specify the actual function, they'll just say it's, for example, y squared dx. Here's an example of a functional. So depending on the function I get, I can substitute it to y squared. For example, so this is called a functional. And so our notation for a functional is going to be strange, because instead of using parentheses like we normally use functions, we're going to use square brackets. So this functional is going to take a curve called y and produces, and this is associated with an integral that takes from x equals a to b. So let's be very specific what a and b is. So for example, let's say this 1 to 2. So here's an example of a functional. We could have other functionals. Here's another functional that takes a curve y is equal to f of x, and it produces an integral from 0 to 1, but we've now taken y squared plus y prime, and let's square it, and dx. So let me try some functionals just to understand this idea. So examples. So here's the first functional, f and g. G's are functionals. Notice square brackets. We'll be using square brackets for functionals. So functionals take an argument. So let me draw an arrow right over here, line. So let's calculate what the functional of sine of x is going to be. So the functional basically says the functional f takes an integral x is equal to 1 to 2, calculates y equals sine x, so this is really sine x squared dx. I won't calculate this integral, it's not important, but the idea of a functional. So for example, if somebody else gives you a different functional, same functional but a different curve, for example, simply put x, then this integral is x is equal to 1 to 2 of x squared dx. So based on the function we passed, right, we're going to get a number out, whatever the number is. So here's another example of g. The g functional basically says that let's pass the function x. So the functional at x is equal to the integral taken from x is equal to 0 to 1 of x squared plus, what's the derivative of x? 1. So this is 1 squared dx. I won't actually solve these integrals, it's not really important, but the definition of a functional is. So the functionals that we're going to be interested in for variational calculus, right, are basically functions that have an integral with some kind of an argument, an integrand, and that integrand basically uses the function, right, that's passed as an argument to the functional. So basically the idea is that we want to extremize, so let me give an example of something that's kind of useful. So let's do it graphically. So imagine that we start from x equals a, and here's gamma, a path that takes it to a point x is equal to b. And our problem is we define a functional, and we'll say here is functional that takes a curve y is equal to some function of x, and it calculates from x is equal to a to b and some integrand. So here's our integrand that basically might be a function of y, might be derivatives of y, might be even higher derivatives, but whatever it is. So our problem is this. I'd like to find the best path that basically extremizes this functional. So I'm going to get back a number for various functions. For example, gamma 1 is some path. Here is gamma number 2 is another path. Gamma number 3. They all start and end, and hopefully I have to make sure they are functions, right? So sorry, it doesn't look like a function if it's, so let me do a function, make sure that the vertical line test makes sense, and maybe this is slightly off, so maybe we should draw it like this, and hopefully it looks like a function. So here is gamma 3. So we can calculate these numbers for various gamma 1, gamma 2. So here is gamma 1, first curve. I'll get a number. So this is a number. I'll compare it with another number for gamma at 2 and gamma at 3. And one of these, right, might be a minimum or a maximum, or it might be some kind of an idea of an inflection point, but based on the different curves, right, we get different values of these functionals. So these functionals are gamma f at gamma 1, f at gamma 2, gamma 3, gamma 4, gamma n. And one of these, right, might be a minimum or a maximum. And if it is, right, that's my purpose. In variational calculus, we're trying to extremize this functional, which means trying to find a maximum or minimum in one of these curves. So our problem is find the curve, find the best curve that extremizes the functional, or finds the extremize doesn't mean that it's actually a maximum or minimum. It might be a critical point, but the basic idea of doing maximum minimum from your first year calculus classes, right, is exactly the same thing, but we're now working with curves. So before we were actually looking in first year calculus, when you're doing maximum minimum, right, you'd find the critical points. That's what slope is, the tangent, right, of a curve, right, at maximum, minimum, or inflection points, right, are basically is equal to 0. Our basic idea, we're trying to find those external points also in variational calculus. But so let me erase this, and let's try to extremize this problem. And so our problem in variational calculus, the first problem is that, so we're given some functional. Oops, remember it's square brackets, so I made a mistake there. So y, and let's assume, right, that in the first example, I'll assume that this integrand starts from point A to B, and it's a function of the independent variable x, and it's also a function of y, and also the derivative of y, first derivative of x. And because dy dx is very painful to write, I'm just going to use Newton notation, which is really a single dot. So just note that dy dx is going to be denoted by a single dot right above y. And so the idea is that, so imagine what we're trying to do. We have a point at starting at x is equal to a, and we're trying to find the best curve that extremizes. So we don't know what the curve is. So here is x is equal to b, x is equal to a, x is equal to b. And so here is, so let's call this curve, right? Let's call it y1. So this is y1 at x. We'll call another curve that's close to it, right, as y2 at x, which is y2. So I'm denoting the first curve that's very close to y2 as y1, y2. We define the variation of the curve y, right, of y1 actually, but is equal to the difference between well, we have to call 1 is y1, y2, but I'll just call this y2 at x minus y1 at x. So this is called a variation of y of the curve y. Now there's several ways of doing these calculations, and I'd like to do it in terms of a physics perspective. And there are other variations where actually this variation is generalized into an epsilon, for example, and n at x, where epsilon is a small number and n at x is a function. So the difference between these two is a small epsilon times n at x. And we could do that, but I'm trying to teach you some physics notations in algebra, right, so that we can simplify calculations. And so I'll actually use the variation of the curve instead of the epsilon n at x, even though like many textbooks do that, and it's actually more proper. But I want you to feel more comfortable with the notation that we use in physics, variations. So this is the variation of the curve. So let's ask ourselves, okay, what is the variation of f? So let me see if I can create some space. Yeah, so what is the variation of f? The variation of f, right, is nothing more than the difference of f at y2. I'll use y2 first, and I'm sorry I made a mistake. I should be using square brackets. So this is y2 minus function at y1. So remember what this is. So I'm trying to get you used to this symbol called the variational symbol. So this variation, right, means that this is really, the first is an integral from x is equal to a to b of I at x, y1, and you'll get used to this, but you won't write these steps, but I'm going through this process to make sure you understand. So this is y1, and I'm sorry, that's supposed to be y2, so I'll erase that, put a 2 minus the integral taken from x is equal to a to b of the integrand of x, y1, y2 dot dx. And we know that the integral, we can actually move the integrals together. So this is now x is equal to a to b of the difference between two different functions, x at y2 minus y2 dot minus the integrand of x, y1, and y1 dot dx. And do you notice it's a difference of two functions again? And so we're saying that the variation of f, so let's summarize this. So if you think about it, this is the difference between two functions, and that's what the variation is. It is a difference of two curves, the difference between two curves. And so what you're saying is that the variation of f at y, so I'm putting it back in, is equal to, notice, so I'll put the variation first in here. I'm rewriting this, x is equal to a to b. So we're building up an algebra. Well, there's no multiplication here, so but we're actually building up rules, right, for manipulating with variations. So it's not technically an algebra. So this is the difference between integral of x, y, y dot dx. And so this statement says that that's really x is equal to a to b, and the variation of I, x, y, y dot dx. So notice that I've taken the difference between two things, and the difference, right, is part of the integrand. And that integrand, right, means that's a variation. So it means that the variational symbol, right, can be taken into the integration. So now we're looking at the difference of two things. But remember, what is the difference of the integral? What is the difference of I? So what is the difference? y2. And it's really the difference, which is Remember, I'm going to write this out in explicit detail, and then I'll redo this calculation over again with variational notation. But I want you to go through the steps because I find a lot of people don't go through these minor steps to make sure you understand. And these are the minor steps to actually understand how to use variations properly. So the variation is really the difference between Ix y2 dot minus the integrand x y1. Hopefully this is on the screen. Yeah, it's good, still good. y1 dot. So that's the variation of I. But this variation, notice the x's don't change, and we can actually do a Taylor difference expansion, right? And so we're actually saying that, so if somebody asked you what is the, so if this is the change in I is equal to the partial of I with respect to x using a chain rule, and say delta x, and partial of I with respect to y, delta y, and partial of I with respect to y dot and delta y dot. And the only thing is that x doesn't really change, so this is actually 0 because x doesn't change. So this is the change in I. So we're trying to build up this. What is this? So what you're saying, right, is so the change in I, the difference between two functions, is equal to approximately the change in the I with respect to y with change in y. So this is your chain rule, and delta y. So with our variational notation, right, this would mean that the variation of I is given by the variation of I, sorry. So again, you got to remember one more thing. I reduced my notation a little bit, right? We're assuming that x, y, and y dot are independent. So you got to remember that x, y, and y dot are independent. So this is partial of I with respect to y, variation of y. Notice the x is not there. The x, there is no difference between x's. This function difference differ in y2s and y1s, but not, so this is now the, and I'll be, once I've done this notation, right, I'll come back and redo this whole problem over again in just terms of variational calculus. I'm trying to build you up to understanding how to deal with variations. So this is the partial of I with respect to y dot, and this is the variation of y dot. That's the delta y. Okay, so we can rewrite this in terms of, actually, because I'm kind of pressed on space, actually, let's see if I can do this. Now, what does this mean? The variation of y dot is really the difference between dy2 dot, sorry, it's y2 minus y1 dot, but that's really dx of y2 minus y1, which means that this is really the derivative of the variation of y. So notice the dot has been moved out. The derivative can be absorbed into this. And these are little minor steps. They seem silly, but I'm going through it because I don't see this in much of the literature. Many authors, they actually prefer doing variational calculus, but I want you to get used to using variational calculus in terms of physics. Okay, and so we have that. And at this time, right, let me erase everything and start redoing this whole calculation up to here in terms of straight steps that you would expect in physics. So I'm going to redo these calculations, but now with variations so that you can understand the steps as if you were a physicist working on these problems. So here we go. So we start off with the variation of f is equal to, so the variation is on the outside, and then I bring it in. So I write this as the variation of I with x y and y dot dx, taken from x is equal to a to b. So remember, this is the steps, I'm just doing it a lot faster. Next, I'm going to say that the change in the I is equal to a to b. It was really the partial of I with respect to y, with the variation of y, plus the partial of I with respect to y dot, with the variation of y dot dx. Notice the steps, okay? So be careful. There's no x. The reason for it is, if you look carefully, there is no change in the x values between the two functions. So when you take the difference between two curves, right, for any x value, right, we're not looking at the x changes, we're only looking at the y's and y prime. There is no change, okay? So this whole term in the chain rule, right, drops to 0. So the next operation is, we're going to write this, x is equal to a to b partial of I with respect to y with the variation of y plus, and I'm going to move the dot out, and so the dot, the derivative of y with respect to x, commutes with the operator, and we get partial of I with respect to y dot, and that is the derivative of the variation of y with respect to dx. And remember, that's all that is saying, right, is that the variation of the derivatives is y2, and the difference between two is just nothing more than y2 minus y1 derivatives, and that's the derivatives of the difference. So that's all I did. It doesn't look like I did much, but so dx. Next, we can apply the chain rule on both sides. I'm sorry, I'm going to be applying the chain rule over here, but so I'm going to first write this as separation. So this is delta y dx plus, and then I'm going to put this integral again, x is equal to a to b of the partial of I with respect to y dot. And so basically this integral now becomes the dx cancels because we're looking at a chain rule. So I'm sorry, this is dot. So let's make sure. So these are the steps that I would normally write. And the only interesting thing is that once I get a solution, right, that solution should look very familiar if you're a physicist. So we're going to use the chain rule, and the chain rule basically says that we can write this whole integral. So it's a lot of extra writing. And I'll put it over here. So the chain rule basically says that this minus this is really the integral of the difference of the partial of I and partial of y dot, I'll put a square bracket, with the variation in y, taken from x is equal to a to b. So this is a plus, and then there's a minus integral where I move the derivative. So I'm going to move the differential to the other side, and actually, you know what? I'll divide by, actually I do it the other way around too, so it doesn't really matter. So this is really the variation of y times the integral of the I dy dot. Hopefully you can see this. Yes, it's still on the board. Okay, good. And then I can divide by dx and multiply by dx by a chain rule, and we're left with this. And we can move these two integrals together, and we'll get this. Taken x is equal to a to b, and that's this element, which is partial of I with respect to y, partial of variation, and minus, there's a derivative of x, I'll put a square bracket here, partial of I with y dot, and there's a variation here, and then dx. And then there's one more term here that says plus the integral taken from x is equal to a to b of the partial square bracket, a variation of y. Notice we're integrating 1 with respect to this symbol. So it's a very easy symbol to evaluate. Now, I want you to first note, right? So I'm going to look at this term right over here. So it's a plus, and look at this term right over here. So I know what that is. That's the integral of 1 with respect to that symbol. So this is really the partial of I with respect to y dot at the variation of y taken at x is equal to a and b. So I'm going to have to erase something on the board, so let me erase this. Actually, I just need these 3 lines. I think I don't need. So I'm going to erase this. So remember, we have some path, 2 gammas, 2 curves, y2 and y1, and they all start at the same point, and they always end at the same point curve. So that's what it means. So we're looking at 2 curves. The variation of y is really y2 minus y1. But at the endpoints, they both come to the same point. So the variation at the endpoints is 0. The difference between y2 and y1 at the endpoints of that curve, right, is equal to 0. So this whole term, right, is actually just 0. So that we can drop this whole term. And so let me write down what I've gotten so far. So let me erase this portion. And so that integral, right, factoring out the variation. So we have this. Taken from x is equal to a to b. So this is the variation of f. And the idea is that around a critical point, right, we expect that around a critical point that the variation in f right, approaches 0. It doesn't vary a lot. That's the assumption. Around critical points, the variation of f approaches 0. But how can, if the variation of f approaches 0 for all functions, if you want this to be 0, how can you have the variation? This variation is 2 arbitrary functions which is not necessarily equal to 0. They might be approaching 0, but not necessarily equal to 0. And so this is definitely not 0. And how can this integral of something taken from a to b equal, and over something over the variation, be equal to 0? And the idea is that this whole term right here must be 0. So for the variation in f, changes in f around a critical point, for them to be around 0, that the variation of f around some critical point is 0, or these are not critical points. Critical curve is probably the better way of saying it. So critical curve, right, is that the variation of f for some critical curve, a set of curves that are close to a critical curve, then the variation of f is equal to 0. So critical points, you'd see this in first year calculus, right? But now this is critical curves. So this has to be 0. So we get the variational calculus theorem basically that says that here, that means that the partial of y minus the derivative with respect to x of the partial of I with respect to y dot is equal to 0. So we're getting a partial derivative equation that, so if somebody gives you a functional, so let me summarize this. Okay, so this looks weird. If, so let me erase all this. So what you're saying is that if somebody gives you a functional that has x, y, and y dot, right, then this implies that the differential equation of partial of I with respect to y minus dx partial of I with respect to y dot equals 0. So what you're saying literally is that this is the equation of curve that extremizes the functional f at y. So it might not be a minimum, it might not be a maximum. It might be an inflection curve, if you want to call it that. But at least we know that it's either a maximum, minimum, or inflection curve, much like maximum, minimum points in first year calculus when you're trying to find the maximum, minimum, local minimum and stuff. It might not be a global maximum or a global minimum, but it is some kind of an extrema curve. So this is our first idea of variational calculus. So in variational calculus, and you're probably wondering, wow, this looks really complicated. And the reason that physicists tend to memorize it and they remember this equation, right, is that it should look kind of familiar if I changed x into t. And I said that I, so y is some variable q, and the integral I is the Lagrangian L. And if I do this right, we'll actually see that, hint, 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 this kind of looks like the partial of L with respect to Q minus the derivative with respect to time of the partial of L with respect to Q dot. And that's equal to 0. Of course, I usually write the Lagrangian with the minus in front, so I'll write this with them multiplied by minus 1. So here's a Lagrange equation, or Euler Lagrange equation of motion for a system, right, that has a Lagrangian L and it's got 1 degree of freedom Q. So that's what variation calculus produces for one variation. So I'm going to switch this now to more complicated functions, and you should try to do some of these calculations yourself on pen and paper. But so anyway, we get the Lagrange equations of motion, and they look symmetrical. In fact, we're going to see later that this idea of having an integrand, right? So if I go back to what's the original function? The original function, right, if I had to assume that we could instead, the usual derivation that I give in my notes, right, for the Lagrange equations, Euler Lagrange equations of motion, right, is constructing using something called virtual work. So I derived this from virtual work, but it's a standard technique, and you'll find it in Goldstein textbook and stuff. But so that derivation, right, it doesn't assume that you had variational calculus. So the question is, if this is an Euler Lagrange equation, right, then could we construct a functional that we can actually define, right, and that basically that we extremize and we get the Lagrange equation? It's a simpler idea. Can I build a functional? And this leads to the idea of construction of a functional, and this functional happens to be, so if I substitute I for L, you'll see that this functional has to have a form of L at, and I'll put the T's and the Q and a single degree of freedom, dt. I'll put everything in. And this functional, right, I'll call this A. And the reason for this is that, so we have Q. So this functional takes some kind of a curve and gives you the integral of L. Remember what L is. L is the kinetic energy minus the potential energy, right? Now we already done Lagrange Euler equations. So erase everything. We start with a new definition of Newtonian mechanics. So the Euler Lagrange equation, right, is actually equivalent to Newtonian mechanics. Of course, dissipation is a problem. We haven't still quite solved it yet. But the Lagrange equations, the Euler Lagrange equations, right, of motion, right, can be constructed as saying that we have something called the action functional. This is called the action functional in theoretical physics. And we can construct and say that if I had such an action functional, and that is the integral from x equals a to b of a Lagrangian tq and q dot dt, then I can derive by using variational calculus to get this equation of motion. So the equation of motion is basically nothing more than an extremization of the action functional. And so in some textbooks, right, it's a standard technique of saying, okay, we don't start with Newton's laws of motion and arrive at this, like what Goldstein does, for example, in his classical mechanics textbook, right? We have a definition of an action functional. That action functional, the extremization of the action functional, produces the Euler Lagrange equations of motion. So modern way of dealing with this, right, is that we have something called an action functional, and that is the integral of the Lagrangian. It just happens to be only 1 degree of freedom, but we'll now extend this further. So this 1 degree of freedom, right, causes that the variational calculus produces the Euler Lagrange, and so this is a simpler idea to work with. And that's great because it extends into relativity and quantum field theory and stuff, and so we can start saying that the variation of the action functional, if I can write the Lagrangian in terms of a relativistic form, right, then we have equations of motion, right, for relativistic particles too. And of course at this point in time, right, field theory only works with special relativity, but I'm sure that somebody eventually one day will actually be able to write action integrals for even potentials. But right now, so the general idea is that we have a new idea of we construct the classical mechanics in terms of a functional that takes a path q and integrates, and the variation of this path lead to the Lagrange Euler equation. And if we don't take dissipation into account, then this is equivalent to Newton's laws of motion. And that's kind of a really beautiful set of ideas. So this is now, hopefully I've started getting you thinking about action functionals. So let me now continue this idea of variational calculus with more than one variable, and hopefully you're starting to see so I prefer to use this variation symbol. So I want you to get used to the variation calculus, and you might want to try this for yourself. So you might want to try, so assume that you're given a functional of y, and it's taken from a to b, and calculate, so assume that this is a function of x and y dot, but let's make it 2 dots, double dot, extend it and try it out yourself. So if I calculate the variation of f, you'll do these calculations, and what is the partial differential equation that you would get if this was a y dot and y double dot? Y was a triple dot. Extend this further into triple dots, and you'll get a generality in this, right? And these are important ideas so that you learn how to do mathematics and understand how to play with these variations. But before I actually go into multivariable, let's do some calculations on this, right? So we feel comfortable using this notation. So application, for example, let's do something really silly. So imagine that there is a point x equals a. So let me do a problem, and x is equal to b, and I take some path between those 2 points. Okay, and this curve, right, has a length. I know that the length, right, S, the differential of length, right, is really equal to squared, is dx squared plus dy squared along any differential element. So if this is dx, dy, we can calculate ds. So this is Pythagoras Theorem. So we can say that the length, right, of any curve, right, is nothing more than, if I divide by dx on both sides, you'll see that if we get ds dx is equal to 1 plus dy dx squared. I divided by differential on both sides. And so what is the arc length? S is nothing more than an integral taken from point A to B of an integral that says 1 plus dy dx squared dx. And if you think carefully, right, this length, right, is really a functional. I didn't tell you exactly what the function is, so this is an example of a functional. And so the question is, I want to find the extremization of this functional, right, that takes any arbitrary path. And so if you remember, this is your I, okay, your integration, and we know that variational calculus, right, produced a differential equation. And if you remember the Euler Lagrange equation, you'd actually say, oh, it is the derivative of the independent variable, in this case x, times the partial of the integration with respect to, I'm using y, so it's y dot, minus the partial of I. So you should remember this as a physicist because this is the Euler Lagrange equations. Okay, so the Euler Lagrange is Lagrangian, x is t. Yeah, like Euler Lagrange. This dust is getting to me. I'm sorry, it's a lot of dust in these rags. Anyway, so what is I? So let's calculate. So we're told that I at x, y, and y dot is equal to square root of 1 plus y dot squared. Now, if you take a look at this equation, right, if you kind of remember, take a look, there is no y in this term at all. And if it is, this will be 0. And if this is 0, that means that the derivative of the partial of I with respect to y dot will be something, and the derivative of that with respect to x is equal to 0. And if that's equal to 0, then this partial of I with respect to y dot must be a constant. So I'm just doing the calculation. So here's your I, it has no y, so this must be 0. So the derivative of something is equal to 0. If that derivative of something is equal to 0, then this must be a constant. That's what I wrote down. So that means that all I have to do is, whatever this constant, let's call this k. And that constant k is equal to the derivative of, sorry, it's y dot, so the partial derivative of y dot. And again, I'm kind of assuming that x, y dots are independent of each other. I didn't write it, so I didn't use the abbreviated notation, which is the correct notation, but we know what the independents are. So this is the partial of I. I is given by 1 plus y dot squared to the 1/2. So we can bring this around and say, okay, this is really 1/2, and 1 plus y dot squared to the minus 1/2, and the derivative of y with respect to y is 2y dot, and that's equal to a constant. So we have this weird equation that says, so let's analyze this. So we're trying to find the extremization path, right, of a curve that's between 2 points on a line on the surface. So we don't know what the extremization curve is, but let's find out what it is. So this is a constant. So you've taken 1/2, 1 plus y dot squared to the 1/2 and dot 2y dot, and you might think it's, wow, this is a really complicated equation, right? How can you change y for any value and it's always equal to a constant? Well, that only makes sense, right? We can go through the analysis on it, but if this is a constant, it must mean that this whole curve, right, whatever this function is, you can drop the 2's, right? But whatever this curve is, right, so if we do it one more time, I can just write down. So here's y dot divisible by the square root of 1 plus y dot squared. And that's a constant. But how can this be a constant when y dots are changing? Well, that must mean that this is not supposed to be derived. It means I'm rewriting it. It means that y dot is a constant also. That's the only way that if you change y dots, because y dots are variables, they're changing, and if they're changing, right, and yet it's always equal to a constant, it must mean that y dot is also a constant. And if that's a constant, right, so what is y dot is equal to a constant c? How do we solve this? This is dy dx is equal to c, and we know that this is really nothing more than y is equal to cx plus another constant. Let's call it c2. C1, let's call this C1, okay. So what is the equation of this? Well, it looks like an equation of a line. What we're getting back is an equation of a line that passes through both points. This is the extremization curve. We don't know, and we know that the line is the shortest distance, and so this functional, right, extremization of this functional produces the curve y is equal to c1x, and this is actually the minimizing curve. I can't tell you usually if it's a minimal curve or a maximum curve, or it might be, but in this case I happen to know, right, the shortest distance between 2 points is a line, and this is an equation of a line. So we can actually see we're applying variational calculus to extremize a functional, and that produces extremal curves. So these curves, right, which might be a minimum, it might be a maximum, and maximum, minimum, or an inflection point. Like later we'll see that you might get curves which are like saddle curves, where you have like one in 2 dimensions, one curves this way and then curves this way. So this is but right now I've just shown you that we found the extremization of the distance functional. So remember, here's our distance functional. Extremization of the distance functional between 2 points A and B. So let me use y dot, okay? So y dot squared dx, extremization of this functional, right, gives you literally an equation of a line. So this idea can be extended into 2 dimensions, 3 dimensions, and we'll see that the idea, for example, is, if somebody gave you, so we haven't done this yet, now we're going to do this, right? I'm going to extend the idea of variational calculus to multiple variables, but imagine that somebody gave you a curve, like for example, here is z is equal to x squared plus y squared. And you have 2 points on the surface of this paraboloid surface. It's a paraboloid surface, let's say these 2 points. And I'd like to find the best curve that connects these 2 points. And so maybe it's the shortest distance. And if it is shortest distance, right, the shortest distance along the surface of the curve is called a geodesic. So this geodesic, right, can we find the equation of the geodesic? Well, the variational calculus gives you this. We know how to do it, and we can actually say this is the curve that extremizes the distance functional along this surface, right, is actually the geodesic curve. And hopefully the geodesic is the least shortest distance, but technically the variational calculus right now, right, the information that I gave you, right, doesn't tell you if it's a maximum or minimum or an inflection curve. We don't know that. So I'd have to give you some more math to actually go into the details whether it really is. So it's much like things like if you have in one-dimensional curves, right? So you might say, well, it's got tangent slope is blah blah, and if for it to be a maximum, right, we expect that the second derivative at that point xo is equal less than 0, then we know that it's a local maximum. And if it's some kind of a curve that goes down and it's increasing, right, so we're expecting the second derivative of xo is greater than 0. And then you could say, oh, that is a local minimum. I haven't given you those rules, and it's a little more complex to do that work. But anyway, so the main idea I want to get across, right, is that variation of calculus takes a functional and extremizes to give you curves that'll extremize, a maximum, minimum, or an inflection. So that's the basic idea. So now with this idea in hand, right, let's now extend this, right, to multiple variables. So I'm always going to be working in y and the first derivative. The reason is that we're not going to be working second derivatives because the functions that we work in physics, right, they only go up to velocity. Knowing the position velocity of something, right, gives you enough information to construct everything else. So now I haven't really emphasized that yet, but once I start talking about phase space, right, we'll talk about more detail. But so let's go back into so here's a new functional. So we'll call this f again, but this function takes a curve y, and so actually I'm not going to use y. Maybe I should use the word gamma. So gamma is the curve. Okay, and this gamma curve is now going to take a look at a functional that basically has x, and we'll label this as y1 to yn and first order derivatives. So basically you're looking at an integration, right? So we're looking at surfaces embedded in an n-dimensional space, and so not surfaces, curves that are embedded in y1, y2, y3, y4, so n-dimensional spaces. And we're going to assume that we have the derivative. And that's so taken from, so we're assuming that there's a parametric representation. So I'm going to say that we have a parametric representation of a path of a curve. So I can't draw this in 2 dimensions, but so if this is y and this is x, so y1, you're taking from x to another point, x is equal to a to xb, but we're also simultaneously taking that point as y2 and x space. So we're parametrically representing that curve y1 as a function of x, y2, so it's another curve that's taking from x is equal to a to x is equal to b. And I'm going to repeat this, right, for all of the n dimensions. So we have some point in space. For example, 3-dimensional space, right? We're expecting y1, or I should say, I don't want you to get confused with the x's. I don't want to say x, but the first coordinate, second coordinate, and third coordinate. Okay, so y2 at x. Okay, so hopefully you started getting used to the variations. So I want to do it as a physicist. So I'm calculating the variation of f. So this is called the variation of f, and this variation, right, again, this variation goes here, but it's the difference between curves in basically n dimensions. So we're looking at a curve in y1 and a curve in y2, y3, y4, yn dimensions. So what is that equal to? Well, so we can do the same analysis, and you saw the variational operator moves into the integration. So I've skipped all these minor steps because hopefully you've kind of pieced it together from the beginning of the lecture, and you should try to do it on pen and paper. You're not going to learn anything if you just watch me do everything. So it's best that you spend time actually writing down these calculations, and the reason I'm doing it slowly on these videos, right, is to make sure that you see a certain pace that you get. When you miss it, if somebody gives you, for example, PowerPoint slides, or somebody just tells you verbally, I want to make sure that you're thinking at a slow rate. Most people think at the rate they write. So that's kind of really important. So anyway, so this is the variation of x, y1, all the way to yn, y1 derivative, yn. So remember, the dot represents the derivative in x. So I know I can use the chain rule, but remember, x does not change between the curves, so we're left with that this is really nothing more than, oh, I forgot my a to b. The partial of I with respect to y, and I'll put an alpha symbol here to represent this, and this is the variation of y alpha. And there's a summation symbol right here, alpha taken from 1 to n. then we have also that the variation of I, so remember the independent variables are x, y1, yn, all the way up to yn dot, all the way to yn dot. Okay, so next we have the partial of I with respect to the y to the n, sorry, y to the alpha, and this is a, so I'm using a Greek letter for summation, okay? Hopefully you're going to later use Einstein summation, but for now I'm going to use alpha. Anyway, so this is the variation of y dot alpha and summation of alpha and dx. Let's put a braces around this and we'll erase this and put more space. Okay, so we've done that. Next, we're going to use the chain rule, right? Not the chain rule, integration by parts to move. Well, first I'm going to move the derivative out. So I'll write those steps in. So here's our summation, alpha taken from 1 to n. Yeah, I do make a, and it's lowercase n, so yeah, but that's okay. So this is the partial of I with respect to y alpha, variation of y alpha, plus here is alpha is equal to 1 to n. And I'm taking now this as partial of I with respect to y dot d dx of the variation n. So hopefully you remember exactly what these things are coming from, okay? So you should review the beginning of this video and to double check, make sure you understand why I can move the derivative out. Okay, so I moved the derivative from the inside into outside the variations. The variation is commuted with the derivative. Okay, and now we're integrating with respect to x. Next, I'm going to do a integration by parts on this term. So hopefully I have enough space for doing everything. So this is sigma alpha is equal to 1 to n of the partial of I with respect to y alpha. I know it seems boring, but it's the hardest part as a physicist, right? Repeating something over and over again without making mistakes. It's the hardest part for me. Anyway, so hopefully you can catch my mistakes. So this is now, I'm going to move the summation. I'm going to move the summation out. And we're left with the integral of x is equal to a to b. I'm going through these steps very, very closely. So put a parentheses around this whole thing. So I'm going to pull out the summation sec. So this is the partial of I with respect to y dot, and I forgot the alpha, so the alpha of the variation of y alpha minus taken from x is equal to a to b of the variation of y alpha, the derivative of the x. Actually, I actually do 2 steps at the same time, but it's okay. I'll do it the long way. Then this is the partial of I with partial of y dot alpha. Okay, and so this is the square bracket that we terminate over here. So we know that the variations at the endpoints, right? Remember, the integral is 1 with respect to the symbol, and so we get back the symbol at the limits I've taken x equal to a. But the variation of the curves at the endpoints, right? This is all 0, and so this whole term is 0. So, and I'll pull out the sum on the left-hand side to write, hopefully, yeah. So this whole integral now becomes the summation of n. Alpha is equal to 1 to n of an integral of partial of I with respect to y alpha with parentheses minus d. So with respect to, so I'm really multiplying by dx and multiplying by dx. So we're using the chain rule. We're chaining this in terms of x. And this is the partial of I. Hopefully do I have enough space on the screen? I hope so. So here is y alpha dot parentheses, and we're left with, I forgot the variation. Sorry, the variation symbol, which is partial of y alpha dx. Did I get that? Yeah, I did. So we did a whole bunch of calculations and it took a little while. Yeah, writing. And I wish I had a larger board, but I don't. And I'd have a real problem like moving board to board even if I did, because I don't have a special service for moving the camera in a certain direction. So anyway, so the variation of f, so let me erase this portion right here and let me summarize what we've done so far. So what you're saying is that the variation of f, which is here, is equal to the summation of alpha taken from 1 to n of the integrals of partial of I with respect to y alpha minus the derivative with respect to x. So, and I forgot the alpha, so here. So you're summing up these integrals for all variation. And so when is the variation? So for critical curves, right, or there's critical paths, right, is when the variation of f approaches 0. If the variation of f is approaching 0, right, then this means how can this be 0 on this side? Well, but this is variation of curves that are really can't be generally not equal to 0. So this is usually generally not equal to 0. So the only way this is possible, right, is if the integrand, right, is 0. And so we get a differential equation that says the partial of I with respect to y alpha minus the derivative with respect to x of the partial of I over partial of y dot alpha is equal to 0. And you might say, wow, that looks complicated, but remember, as a physicist, right, you might remember these equations better if you remember that these are the Lagrange Euler equations. So the Lagrange Euler equations, right, is the same idea. If you had an action functional, right, and I'll actually redo that in a sec, but we can rewrite this equation in a form that a physicist would probably understand better, which is dx partial of I with respect to y dot alpha minus the partial of I with respect to y alpha is equal to 0. And remember, so this equation, right, should remind you when x is transformed into time and y alpha coordinates are defined in terms of q alpha, and the I is in terms of the Lagrangian kinetic energy minus the potential energy, then we get the Lagrange equations of motion. So this is the standard equation that you should always use when you're looking at multiple variables. So if you have a functional that has an integrand of multiple dimensions and with a dependence variable, and we're trying to find the curve that extremizes this functional, we use this equation. And it should be familiar to you. So as a physicist, I always remember this equation because I always remember the Lagrange Euler equation, because that's what a physicist does, right? He uses those equations to construct classical mechanics. Anyway, so I know this is a long lecture, right? We exceeded, seems to be exceeding an hour and 5 minutes, but So this is called variational calculus, and I could extend this to two-dimensional surfaces and volumes and areas and stuff. So if we had a functional that has in two variables and we're trying to find the optimal surfaces, I haven't done that. So, but this is what we need to do in physics, and so the variational calculus is very specific. We're looking at curves that are extremizing functionals.